We'll talk just a little bit more about similar triangles. We already did a little bit of this. But similar triangles actually wind up being a really common tool we use for solving real-world problems. We noticed that if we had a building, and we wanted to know how tall the building was, how can we do it? One way to do it is with shadows. If we know that we have a meter stick, so if we know we have a 1 meter long stick and it casts a 2 meter long shadow, we can compare that to the shadow of the building. So if the shadow of the building is, say, 48 meters, we notice that the height of the building, we know that the triangles, we know that they both form right angles, they both have, the shadows have the same angle, and so we know that by angle, 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 they have to be similar triangles, and so that tells us that h divided by 1 has to match up with 48 divided by 2. And so we now know that h has to equal 24 meters. So that's a nice easy version. If we had something like two triangles arranged like this, if we know that this side is 3, this side is 4, and we know that this is, let's make it 6 and 12, we notice we might ask what are the distances A and B? And so you have to be a little bit more careful. We notice that we can't just say 3 divided by A and 4 divided by B equals 6 divided by 12. That's not going to work. What we can say is 3 divided by 3 plus A has to match up with 12, where'd it go? 6 divided by 12. And that has to match up with 4 divided by 4 plus B. And so we notice we're taking the shorter side divided by the longer side equals the shorter side divided by the longer side. And so we can set that up as two different equations. We notice that we can set it up as 3 divided by 3 plus A equals 1/2. Cross multiply, we know 6 equals 3 plus A. Subtract 3. We know that A equals 3. And then you might guess that B has to be 4. We notice that we can say 1/2 equals 4 divided by 4 plus B. So 4 plus B equals 8. And so B has to be 4. So that's one where it's a little, sometimes you can see the common ratio, sometimes you can see that scale factor. It's not always that obvious. You'll sometimes see things where you've got a common side. So if we had something like this, where we have a common side, you might know that, what do we want to say? Might make this 8, 6, and then we notice that if we happen to know, actually we don't even need the 6, what we end up noticing is that if we happen to know that two of the angles match, actually all we need is the one angle. Oops. All we need, if we happen to know that these are both 8 and these two angles match, we know that we've got side angle side. And so the two triangles have to be congruent. So if we knew that one side was 4, the other side would have to be 4. So that's one we can do with congruent triangles. We're not going to get many of those. We'll do one more with similar triangles. So one I think we kind of talked about before, one of the classics, is if you're just told one triangle is 4, 7, 12. In fact, we don't even do all that. We can just say 4, 7. And the other triangle is we're going to make it 12, 30. We can figure out the third sides. So we notice that the common ratio has to be common ratio is k equals 12 divided by 4 equals 3. And so if we just give these sides names, call that x and y, we know that y divided by 7 has to equal 3, and so that means y has to equal 21. We know 30 divided by x has to equal 3, and so we can see 30 has to equal 3x divided by 3, and we see that x has to equal 10. One more little thing we'll just mention as a preview of a future section. As I mentioned, all of this is rooted in trigonometry, and so something that's kind of interesting is if I draw an arbitrary triangle that was 4 by 5 by 7, and I wrote down 30 degrees, 50 degrees, and make it 40 degrees, 50 degrees. Nah, we don't do it that way. Let's do it 70 degrees, 50 degrees, 60 degrees. I can write those numbers. But this triangle physically cannot exist. We could have a 4, 5, 7 triangle, so we could draw the triangle 4, 5, 7, so this can exist. But it'll have different side lengths. But has different angle measures. And similarly, we could have a triangle that had angle measures 50, 70, 60. But what we're going to notice is that if we called this A, B, C, what we can find out is that BC divided by BA cannot equal BC, so length of BC divided by length of BA cannot equal 5/4. And so we cannot have a triangle with those same 3 side lengths and those 3 angle measures. And again, that goes back to trigonometry. We don't need to know the details of that just yet.